So starting with problem 3.10 now, it asks us to determine a molecular formula. Well, hopefully, if we just look and see that this compound only has carbon, hydrogen, and oxygen, we can see that we have a covalent compound. We only have nonmetals in this substance. So that should be a big clue that we have a molecule that we're going to have here. So the molecular formula might not be the same as the empirical formula. We're going to treat this problem the exact same way as we did the previous problem. The first thing that we need to do is figure out the empirical formula. What is the simplest whole number ratio between the carbon, the hydrogen, and the oxygen? After that, we'll have to compare that molar mass of the empirical formula to the actual molar mass of the compound and see if they're the same. If they're the same, that means your empirical formula is the same as your molecular formula. If they're not, they should be off by a whole number, and that is the number that you will scale up your empirical formula by. If that didn't make sense, play this back at the end after we've solved the problem, and hopefully it will make a little bit more sense. But again, we're going to treat this problem the way that we treat all of our problems. We'll start by writing down information that we know, and we'll figure out where we want to go. We're given, in this case, mass percent. So we're given mass percent data. So again, that's a little bit different from our previous problem here. Our previous problem, we were actually given mass data. So if we're given mass percent data, we need to go to grams by using the in every 100. And I'll explain that in just a minute if that doesn't make sense initially. But once we get to mass data, now this becomes just like a problem we had before. Okay, so we can have mass percent data. We can get to mass data in grams using our concept of in every 100. Then we can use the molar mass of each element to get to a mole. We can get to moles of each substance. And then we can get to the empirical formula by taking the simplest whole number ratio. And then going between the empirical formula and the molecular formula, we need to compare the molar mass of the empirical formula with the molar mass of the given of the substance. And we have to ask the question, are they identical? And if not, what is the ratio, the factor that they are off by? Now I know that seems like a kind of a crazy roadmap to start, but let's start working through this problem and hopefully you'll see the path that we're taking here and it makes sense. And again, the more that you maybe practice problems like this or review problems like this, you'll realize, hey, if I need to determine a molecular formula, here's kind of the information, the path that I have to take. Remember, the difficulty of these problems has to do with how much of this path you have to walk. A simple version of this problem would be if I gave you the moles of carbon, hydrogen, and oxygen. Then you'd only have a short walk to take. A little bit of a longer walk is if I gave you mass data, like we did in problem 3.9 that we just did. This problem adds another level of difficulty by giving mass percent data. Okay, so what we need to do here is use this concept of in every 100 because they give us that there's 40 mass percent carbon. Well, what this really means, if we imagine if we had 100 grams, so imagine that we had 100 grams of this lactic acid. Does it make sense that we would have 40.0 grams of carbon, 6.71 grams of hydrogen, and 53.3 grams of oxygen, right? Part over whole would be 40%. Part over whole would be 6.71%. Part over whole is 53.3%. So this is how we can use percent data. Remember in one of our previous sample problems, we actually had to calculate mass percent data. So in this case, we're using mass percent data and we're extracting back out mass data. Now that we have this mass data, we're ready to go on and treat this problem kind of like what we had here. Okay, so let's go ahead and do that. We've got 40.0 grams of carbon. Again, to convert this into moles, we use the molar mass of 1 mole of carbon. So we've got 12.01 grams of carbon is 1 mole of carbon, 3.33 moles of carbon. 6.71 grams of hydrogen. 1 mole of hydrogen is 1.008 grams of hydrogen. That's 6.66 moles of hydrogen. 53.3 grams of oxygen. 16.00 grams of oxygen. 1 mole of oxygen. And in case you're confused or wondering where we got this information, remember this is information directly from the periodic table. These are the atomic masses of these elements. So this one equals 3.33 moles of oxygen. Remember, to get to empirical formulas, we're going to divide by the smallest number. So we're going to divide everything by 3.33, and we get CH2O. Wow, remember, this is a carbohydrate. All carbohydrates have 1 carbon for every 2 hydrogens and every 1 oxygen. That's why they called them carbohydrates, because it looked like it was a hydrated version of carbon. Okay, so now the idea is we need to see what the empirical formula is. Once we got to the empirical formula, we had to compare the molar mass of the empirical formula to the molar mass that they give us of the substance. So the molar mass of this, again, just adding up these, is going to be 30.03 grams per mole. They give us up here in the problem that the molar mass of lactic acid is 90.8. So molar mass of lactic acid equals 90.08 grams per mole. And as we had up here in our roadmap, we needed to ask the question, are these identical? If that's the case, then our molecular formula is equal to our empirical formula. If they're not, we have to see the factor that they're different by. Hopefully everybody can just look at these and see that this is a 3-fold factor increase. So what that means is we need to scale our empirical formula, so again this is our empirical formula, by 3 times in order to get to our molecular formula. So that means we're going to have C3H6O3. A great check that you can have for these kinds of problems, go through and calculate the molar mass of this. You will get 90.08 grams per mole, or fairly close to it. Go back if you want and actually make sure that this has 40% carbon, 6.7% hydrogen, and 53% oxygen. There's kind of that built-in internal check with these problems. Now, you might not necessarily have that much time on a quiz or an exam to go back and do that, but as you're going through these on your problems with your homework, go ahead and check and confirm for yourself that that will work. So again, checks for this are to go back and recalculate the molecular weight, and then you can also recalculate the mass percent. And it should be something that you get back to these original given parameters.